Hello, everyone. My name is JP Metcalf, and I'm a sales engineer over at L3 Harris Geospatial. Today, I want to present exploring agricultural remote sensing data in the ENVI software. So let's get started. Here's a quick look at what I'll be covering in this video. I'll talk about different sources of remote sensing imagery and how the spectral, spatial, and temporal resolution might influence your data use decision. I'll then go over the uses of remote sensing imagery in agriculture. And then within the ENVI software, we'll look at time series analysis using optical and SAR, as well as UAV tools, crop science, and the deep learning module. And then towards the end, we'll look at a croplands data layer estimation use case. So let's jump in. So the rate at which you can monitor agricultural fields using imagery depends on the platform. Satellite imagery can have revisit times over a given area ranging from weeks for a single platform or a daily revisit for a large constellation like Planet or Capella. With their high orbital altitude, some satellite view angles can cover very large areas at the expense of high spatial resolution, while others sacrifice that large area coverage for that high spatial resolution. Imagery collected on aerial platforms can get down to a few centimeters with multispectral cameras, although the revisit rate can be low due to the cost of flying an aerial sensor. And imagery from unmanned aerial vehicles or UAVs will often be on the orders of a few centimeters resolution with multispectral, even hyperspectral cameras. So from fixed wing to rotor copters, UAVs can be used to capture relatively small areas at a high enough resolution to count small crops with a frequent revisit rate. Whether your imagery is captured from a satellite, aircraft, or UAV, the remote sensing software suite ENVI can process your imagery and produce a meaningful solution. ENVI uses scientifically proven analytics to deliver expert-level results. For highly specialized tasks, available modules can be called in ENVI to perform processes like atmospheric correction, feature extraction, or deep learning, to name a few. Everything I'll present from here on out can be processed in ENVI. So analyzing vegetation using remote sensing data requires knowledge of the structure and function of vegetation and its reflectance properties. This knowledge enables you to link vegetative structures and their condition to the reflectance behavior in the ecological system of interest. ENVI has several vegetation-specific indices built in, and the number of indices available can depend on whether the input data is multispectral or hyperspectral. Nearly all of the tasks shown here can be used in an automated fashion. So let's start looking at optical and SAR. Here's a comparison between the two. The optical image is a Sentinel-2 scene from June 20th, 2018 on the left-hand side. And in that image, we can clearly see the areas of green vegetation and barren fields. With analysis processes like spectral indices and time series analysis, we're able to find out possible crop types and track their growth and change over time. On the right is a Terasar X vertical out, vertical receive image from June 18th, which is a few days before the optical image. And looking between the two, we notice some differences. So looking at the red circle for one example, even though all these areas show up as a green gradient or barren in the optical image, we have a large difference in backscatter in the SAR. The backscatter of SAR is affected greatly by crop type, soil moisture, and geometric effects, thus making certain vegetation appear very different from similar green-colored vegetation around it. Areas that are very bright white have a high intensity response. Think of it as the more the vegetation, the denser, the larger the leaves, and other factors, the more intensity is going to be scattered back to the satellite. On the opposite side, if it's bare soil or wet soil, it will act similar to flat surfaces and reflect most of the backscatter away, which would make it appear very dark in imagery. Here I have 4 Sentinel-2 images spanning multiple dates over a field highlighted in red. Over a 3-month period, these are the only usable Sentinel-2 images because of cloud cover and things of that nature. And you can see the large gap in between the barren field in June, and the beginning of growth on August 4th, and the greening in late August, and suddenly an empty field in the end of September. We're missing a lot of crucial information about the growth cycle with the limited access of this optical data, so let's see what SAR can give us instead. Now, we're looking at the field we just viewed with our 4 scenes of optical data with a few different SAR sensors. At the beginning of this time series, we see high intensity responses. This is due to plowed soil in preparation of the planting of the field, as we saw in the June optical image. In the beginning of July, we see a minimum, which is highlighted by the green line. This minimum is related to the sowing stage of the cereal field. After that, the responses slowly increase as vegetation grows and the intensity of our backscatter off of the canopy and structures increase. In mid-September, we hit a peak in the Sentinel-1 data. This is caused by the harvesting and upchurning of the soil, as well as the leaving of some of the vegetation debris on the field. Soon after, with the red line, we see a decrease in TerraSAR X, which occurs when harvesting is finished and the soil has returned to its normal state. In the SARscape Intensity Time Series tool, the first output that you get is a multi-band image, where every band is a different date of the SAR imagery. It automatically orders them from earliest to latest image, so you don't have to worry about moving dates around. And the image on the center is made of 3 different dates, shown as red, green, and blue bands. This allows us to easily view changes within our scene and pinpoint how certain fields are performing during a certain time period. It looks pretty, doesn't it? Here we have a few fields highlighted in blue, light blue, and red so that we can take a look at the temporal separability of multiple crops. Similar to the optical data, we can use the image made up of multiple dates to track the changes over the entire fields and compare them for analysis. We found 3 fields of interest, and using the time series viewer tool, we can make a comparison of their growth rates over time. Changes in the intensity show us how these fields differ and how this output can be used in tandem with optical data to get an understanding of SAR optical crop interactions with their best practices. With this, you can track temporal changes from crop to crop, field to field, or even over an entire scene to see how the crops are growing and how they compare to each other easily. We can also generate a classification of specific field types from the time series. The example on the screen used training data over the entire time series, shown on the left, to find all fields of wheat, shown on the right. There is a little bit of confusion with some of the other crop responses, but overall, this quick classification did a great job of finding all of the other wheat fields. And then it could be used to create shape files and track their temporal changes for comparison. So now let's talk about the ENVI crop science module. So the crop science platform contains remote sensing analytic tools for precision agriculture. Crop science was made to work with agricultural imagery specifically, and it's data agnostic, meaning you can pass any type of raster imagery in. All of the tools are available as tasks, so you can create large automated workflows to extract crop information. Once you've defined and counted your crops, the crop science tool can produce all sorts of metrics to get a handle on your field. Crop science can count individual crops and generate a vector file, including the crop diameter. Here's an aerial image of an orchard where each individual tree has been delineated. Once the crops have been identified, you can use spectral indices to compare each plant to the performance of the whole orchard. Inside the crop science module, we have the row finder and gap finder. And the row finder does exactly that. It finds rows of crops, and it can also produce a vector line for that row. Crops outside of that row can be removed from any further analysis, things like weeds. And the gap finder will evaluate the crop locations as a grid and determine where gaps are present. An image containing your crop might have adjacent pixels that you might not want in your analysis. In crop science, you can delineate your field of interest and then run hotspot analysis to find trends in your field and your field only. Here we show 3 different indices and use hotspot analysis to determine global spatial statistics within the field. And in developing hotspots, you can pass in 2 indices to determine if areas greatly depart from the mean index. Here are two NDVI images where we want to see if any significant change has occurred in the health of the field. The first dates NDVI image shows a uniformly high NDVI value for the entire field, with some stress developing in the southern part of the field a few days later. With developing hotspot analysis, we see that the northern area actually had significant positive change, while the stressed area shows the negative change was significant. Moving on, let's talk about the ENVI Deep Learning module. It's relatively new to the ENVI suite of tools, but within this module, you can train a model to find specific classes based on physical features beyond just their spectral component. A deep learning workflow basically involves the generation of training labels by delineating groups of pixels that represent your class of interest. Then you would expose the model to the labeled imagery so that it learns how to find your classes. You can then use the trained model to quickly find your classes in similar imagery. In our first example for deep learning, we're trying to mark the presence of weeds, because weeds can contribute to a decrease in crop yields. So to control that weed growth, it's important to know where they're growing in relation to the planted crop. Spectrally, crops and nearby weeds can appear identical when viewed in true color and near-infrared imagery. And deep learning was found to be very useful in identifying crops and weeds by detecting subtle differences in their shapes and patterns. In this example, UAV collected imagery was used to train a model to identify the differences between a sugar beet crop and the surrounding weeds, leaving the soil unclassified. The images on the right show the activation values for weeds and sugar beets. Think of the activation images as a pseudo-probability of that particular pixel belonging to that class. Deep learning can be used to find spatial patterns in imagery and provide an ideal solution for locating fields with irregular shapes, such as center pivot irrigation. In this example, a deep learning model was trained to find circular irrigation fields found in Sentinel-2 imagery. Notice that there are numerous rectangular fields in the image that remain unclassified. Here's another example of deep learning applied to planet satellite imagery. At the time of this project, the U.S. Department of Agriculture did not yet release the 2020 cropland data layer. So what we wanted to do is estimate what the layer would be for 2020 by creating a deep learning model utilizing the past few years of PlanetScope 4-band imagery and previous published cropland data layers for corn and soybeans. The cropland layers were used as training data so that the model would learn the differences between corn and soybean. And here we have our 2020 model that we used. So the entire multi-step workflow for the deep learning training and classification task was put into an ENVI model, which is shown on the left. The input raster data inputs are labeled in blue, while tasks are labeled in yellow. After running the model, the predicted croplands classification layer for corn and soybeans is generated for an image collected in 2020. And that's what I have. Thank you for your time. And if you have any questions about the content presented, please email me at jp.metcalf@l3harris.com. And I hope you enjoyed this presentation. Thank you.